Yeah, good evening to you all. Today we're going to see the lecture number 29, in which I am going to present you the very important topic, very important, concept of this time response of second order system. So, in our previous presentation, we have seen the standard form of the transfer function of a second order system that we have seen C of s by R of s, that is equal to omega n square by s square plus 2 zeta omega ns plus omega n square. That's what the transfer function we have seen. From there we have seen, depending on the zeta values, that system can be classified into four categories. That's what we have seen. So for zeta equal to 0, it is called undamped system. For zeta is equal to 1, the system is called critically damped. Whereas for zeta is less than 0 to 1, that is called underdamped system. And if zeta is greater than 1, that is called overdamped system. So depending on the zeta value, we have seen that four types of cases or four classifications. Out of all these four categories, okay, and okay, just I will write you, I will recap for your understanding. So we have seen that C of s by R of s is equal to what we have seen, it is omega n square by s square plus 2 times zeta omega n into s plus omega n square. This is what we have seen. This is what the standard form of transfer function of a second order control system. So here, depending on this zeta, we have zeta equal to 0, then that is called undamped system, and zeta is equal to 1, that is called critically damped system, and zeta value is less than 0, is less than zeta is less than 1, that is third condition. Means this is the first condition, this is the second condition, this is the third condition, okay, and the fourth condition is zeta is greater than 1. We have seen this already in previous presentation. This is called undamped. This is called undamped system. Clear? So this is called critically damped. This is called critically damped system. Critically damped system. This is called underdamped. This is called underdamped system. Okay. If it zeta is equal to 1, this is called overdamped. This is called overdamped system. So based on the zeta values, we have four types of classifications of our system. Out of all these conditions, as I have explained you in our previous presentation, the third one is very important. The third case, this is very important one. Therefore today I am going to present you that the response of a second order system, the response of a second order underdamped system. Okay, the response of a second ordered underdamped system with unit step input. With unit step input, that is what our today's presentation actually. Okay, so now today just I will explain you that. Let us see the response of a response or time response. Time response of second order underdamped system. Second order underdamped. This is very important. Second order underdamped system for unit step input. For unit step input. This is what we'll see today. This is nothing but, again, in order to see the response of a second order system for underdamped system. So first let us consider the transfer function. As you know that is C of s by R of s is equal to, it is omega n square by s square plus 2 times zeta omega n into s plus omega n square. This is the standard form of your transfer function of a second order system. Let us consider the standard form of a transfer function of a second order system. That is what this one, call it as equation number 1. Now, what is the value of zeta we are considering? It is a underdamped system. As our system is underdamped, therefore, for underdamped system, we are considering underdamped. Therefore, for underdamped system, let us consider 0 is less than, zeta is less than 1. Is it not? 0 is less than, zeta is less than 1. So, for this condition, in our previous presentation, we have seen what are the roots of this characteristic equation. What are the roots of this characteristic equation? So, for this condition, you have your S1 comma S2 is equal to, we have seen in our last class that minus zeta omega n and plus or minus, clear, plus or minus under plus or minus j times omega n into square root of, what is that, 1 minus zeta square. This is what we have seen actually. This is what we have seen. These are the roots for this condition, for this zeta values. We have seen that the roots of this roots of this denominator, and this is called characteristic equation. If you equate this equal to 0, that is called characteristic equation. And for that, if you obtain the roots, your roots will be like this only. And finally, from this, we can furtherly we have written this also, zeta omega n plus or minus j into all this entire portion we have called it as omega d. Is it not? Omega d is the damped natural frequency, whereas omega n is the undamped natural frequency. So this is what your S1 comma S2 means. These are the roots. These are the roots of that second order system, because these are also one of the important thing that we must consider, where omega d is nothing but this entire portion, omega n into square root of 1 minus zeta square. This is already I have explained you in last presentation. Omega d is equal to omega n into square root of 1 minus zeta square. This is damped natural frequency and damped natural frequency. This is the relation between these two. Clear? So let us keep aside this. Okay. So these are the roots. Now, so we have taken the transfer function, we have considered the transfer function, and after that we have considered the underdamped condition also. With the underdamped condition, what are the roots? And we also know that these are the roots, actually complex conjugates. Remember that the roots are complex conjugates. The roots are called complex conjugates. Now, what we have to consider, what is the input that we are applying to this system? What is the input we are applying? That is whatever unit step input. That means that from this implies you write C expression for C of s. C of s is equal to, take this R of s to the right side of this equation. Then obviously your R of s goes here. R of s into, in everything you write in bracket. That is omega n square by, it is s square plus 2 times zeta omega n into s plus omega n square. Clear? This is what your equation number 2. Let us call equation number 2. So from this first expression, now I want to write the expression for C of S, and therefore C of S is equal to, then this take this R of S to the right side, then that comes here R of S. R of S comes in multiplication, R of S into total this quantity. Okay, now what is your input actually? What is your R of S is nothing but input. What is your input? It is a step input. So for step input, for our unit step you can say, for unit step input, unit step input is nothing but R of t is equal to 1, is it not? Unit step is nothing but R of t. Your R of t is equal to, in time domain, R of t is equal to 1. This implies what? Take Laplace transformation, R of s, that becomes R of s, 1 becomes 1 by s, right? So by applying the Laplace transformation to this R of t is equal to 1, your R of t becomes R of s, 1 becomes 1 by s. This already I have explained you. Therefore, please refer our previous presentations. There you will get the information about this. Therefore, now R of s is equal to 1 by s. Substitute this parameter R of s equal to 1 by s. This much quantity, you substitute this 1 by s here in this expression. Therefore, what you will get? I will erase this. What you will get? So substitute that in a R of s. Then you will get, this implies C of s is equal to, here R of s is nothing but your 1 by s, is it not? Bracket, write the entire thing as it is, omega n square by, it is s square plus 2 zeta omega n into s plus omega n square. There is a simple mathematical calculation is there, that's all. There is a simple mathematical this thing is there in order to find out the response, and from this actually it is called omega n square into s into, this is the form. And you can write in partial fraction. If you write in partial fraction, you know that definitely it is called a by s plus, here it can be written as b into s plus c by this entire s square plus 2 zeta omega n into s plus omega n square. Like that we have to write. That is your C of s can be written as like this in partial fraction. So this can be written as like this. And as we have seen in our previous presentation, here you have to find out the a value, what is a value, and then you have to find out what is b value, and you have to find out what is c value. How? It is very simple. In order to find out the a value, you multiply C of s. C of s is nothing but this entire portion is your C of s. So, okay, in order to find out a value, just multiply this C of s with s. This s is multiplied with C of s. C of s is nothing but this entire. Therefore, s is multiplied with, therefore, s into C of s. Therefore, s into, okay, I will write this for your better understanding. In order to find out a value, a can be obtained as a is equal to multiply s into C of s. S into C of s, where s equal to 0. Substitute s equal to 0 in that. This implies what? Yes. What is C of s? C of s, no, this entire thing, no? This entire thing multiplied by s. Yes. So means that s and this s will cancel out. Is it not? S and s will cancel out. This will remains there. In this, substitute s equal to 0. So here 0, here 0, then omega n square by omega n square. You will get 1. Therefore, your a becomes 1. Clear? A value becomes your 1. And similarly, in order to find out your b and c value, then what you will do now? Just you cross multiply these two. A into this one, this entire quantity multiplied by a, plus s into this thing, that is equal to your omega n square. That you have to equate. So a value is 1. Clear? And in order to find out the values of b and c, what you will write, So a into s square plus 2 zeta omega n into s plus omega n square. Clear? Plus multiply this, means S into Bs plus C is equal to this entire must be equal to omega n square. Omega n square. Clear? And from this expression, you have to equate the S terms on both sides one time, and secondly, equate the S square terms on both sides. If you equate S term on both sides, equate S term, okay, by equating S terms on both sides. So what you will get if you equate S terms on both sides? This is S, okay, this is S basically. Then what you will have? A into 2 zeta omega n. Clear? So the S term is nothing but, so A into 2 zeta omega n. Is it not? What is S term here? So here S term is S into C. Clear? S into C means the S term is C is equal to, means S into C basically. Therefore you have to consider S coefficient, means C, that is equal to omega, no, it is 0 because there is no S term on right side, therefore it is 0. This equal to what you will write? What you will write? So here you substitute A value is 1. So already we obtained A as 1, therefore substitute A as 1 here. This is 1 into 2 zeta omega n plus C equal to 0. Therefore from this you can write, this implies, so 1 into 2 zeta omega n is 2 zeta omega n. Therefore C is equal to, you write, minus 2 zeta omega n. This is what your C value. This is what your C value, minus 2 zeta omega n, C equal to. Therefore, by equating the S terms on both sides, you will get C value like this, minus 2 zeta omega n will come. And similarly, equate the S square terms on both sides, means this entire part is the left side, this is the right side. Then equate the S square terms on both sides. Clear? So this is your C basically. Now, if you equate the S square terms on both sides, you will get the value of B. So equate the S square terms. So if you equate the S square terms, so S square term is here A, is it not? A, and here S square means S square, S into S square plus B, means B will there, A plus B. Clear? And what else is there? Is equal to 0, because on right side there is no S square, therefore it is 0. In left side, no, so this is one parameter, one quantity, this is the second quantity, you can say. In S square, this is S square coefficient is A, plus here S into S square coefficient is B, A plus B equal to 0. From this A value you already know, it is 1 plus B equal to 0. This implies B equal to what? Minus 1. This is the value of B. So we already now, you obtained 3 values. A value you have already obtained as 1, that is A is equal to 1. B value is minus 1. C is equal to your minus 2 zeta omega n. Minus 2 zeta omega n. You substitute all these terms in that, and afterwards you take the inverse Laplace transformation to C of S in order to find out the C of t. Okay, just I will substitute these parameters. Basically it is a small mathematical things it involves basically, so nothing to okay. So if you substitute those values, if you substitute those A, B, C values, what you will get, you know, it is A value is 1 obviously, therefore 1 by S you will get, plus what is B value, it is minus 1, therefore you will get minus of S. What is, it is minus 2 zeta omega n. Clear? Yours, okay. So 2 zeta omega n by, it is S square plus 2 zeta omega n into S plus omega n square. Clear? Then here minus and minus is there, take minus as common. If you take minus as common, in next step you can write minus here, and then you can put bracket here, you can write plus here. Means the minus will come here. Again, if you multiply this minus with plus, again minus will come. That equal to that one only. This is what your C of S. This is what your C of S. Now after certain mathematical, I mean formulas, if you apply some mathematical analysis in further, and definitely if you apply the inverse Laplace transformation to this, okay, if you apply the inverse Laplace transformation to this, so then if you apply the inverse Laplace transformation to this, then C of S becomes C of T, obviously, clear. If you apply the inverse Laplace transformation to both sides, C of S becomes C of T, then 1 of by S, if you apply inverse Laplace transformation 1 by S, nothing but 1, it becomes 1 minus, what it will come? There is one expression will come basically. I want to stress you upon that only basically. I will write that expression for you because this is a little bit, it involves some mathematical simplification calculations in order to obtain our interest, our interest of equation, or rather our equation of interest is nothing but it is C of t. Basically C of t is equal to 1 minus, you will get finally e power minus zeta omega n into t by under square root of 1 minus zeta square. Clear? It is sine of omega d times t plus theta. This is what your final expression actually. This is the time response. After little bit mathematical calculation, because I am skipping that everything because that involves a lot of this thing, but however in examination you will not be asked to derive the expression for this. Is it not? Just you have to know that what is the time response equation. This equation you must know, that's all. You are not need not to worry about the derivation part, because in examination derivation will not be asked. Don't worry. So derivation part, they will not ask you the derivation part. Simply you must know what is the response after this for this. So therefore C of t is equal to 1 minus e power minus zeta omega n into t by under square root of 1 minus zeta square sine of omega d. What is omega d here? Omega d is nothing but, already we know that omega d is nothing but omega n into square root of 1 minus zeta square. This is already we have seen. It is a damped natural frequency, undamped natural frequency. Zeta is your damping factor or damping ratio. That is the one formula. And however, omega n is omega n is the undamped natural frequency, zeta is the damping ratio. Okay, omega d already I have explained. What is the theta? Theta is equal to, this is very important. Okay, theta is equal to, actually it is tan inverse of square root of 1 minus zeta square by zeta. This is what tan inverse of theta is equal to tan inverse of whole bracket square root of 1 minus zeta square by zeta. That is what your this value, theta value. This is called theta value. And just note down, you remember this expression. This is what the response, C of t means the response of a second order underdamped system for a unit step. Okay, for unit step. This is what the response of a second order system. Okay, thereby if you can draw the time response, the graphical representation of this one, you will get. So this is very important, means the graphical representation of the second order system. I will explain you that. This is the time response, how it could be. So this is what your C of t, this is what your T of t. This is your time t. This is your output C of t. This is starts from 0. Now, this is what I am going to explain you, that the time response in graphical method. So, just now we have seen that C of t expression, C of t is equal to 1 minus, means 1 is the maximum value actually. Therefore, you write that 1, somewhere your output is 1, no? You write somewhere your 1 is like, here is the 1 value, output, C of t is the output. Here, you just draw a dotted line. You just draw a dotted line here like that. This is what your 1 basically. Clear? And here, so this is 0 to 1. Somewhere in between exactly you will have some 0.5 value, means 50% value, 0.5 value. Now if you can draw the graph, it looks like this actually. It shows like this. Okay, so the graph will be like this basically. So here this is nothing but as t goes on increasing, how the output will changes. So if you see from this, we define certain parameters. Let us say, for example, as the time t is going on increasing, your output will also changes like this, in this way. So this is called here, this is 0.5, no, 50%. So from here you can define one parameter, that is called some time, the time is called as td. This is called delay time. Delay time, this time is called delay time. First I will note down, and up to this one, this is called your tr. This is called your tr. And then here, this is your peak value actually. This I will note down here for your this thing. This is called TP. Clear? TP. And then here, so you can little bit show like little bit of C of t, and here is there no peak, and the difference between from this 1 to this up to peak, that is called peak overshoot, MP, that is represented in terms of percentage actually, percentage of peak overshoot. And then somewhere here your output will be settled basically, it will reaches to, it settles and constant, it will comes, it almost all reaches like that constant. I mean it combines with line 1. Then this is called the tolerance, basically allowable tolerance, allowable tolerance, that is 2% to 5% of tolerance band will be there. So at that particular time, so your output will be settled, that is called TS, that time is called. So I will represent here for your this thing. I will note down that. So for your from here starting point to this, I will call T suffix s basically, and I can call here up to this one, because at this particular time your graph will almost all combines with this 1 basically. The maximum value 1 is there. No? So with so your graph, your output will merges with 1. That is called output is settled. Output is called settled at that particular. So the time at which the graph, the output settles is called settling time. And there is a tolerance band for that. It is called 2% to 5% of tolerance, allowable tolerance. Within, so for that tolerance at that particular time, so your output will merges with 1. It settles there. So this is what basically the graph, and here we have seen so many parameters. The first one is TD. You can able to see na? The first one is TD. What is TD? It is called delay time. It is called delay time. What is delay time? Delay time is nothing but the time which is required for the response. This is what the response actually. Delay time is nothing but that is the time that is required for the response to reach 50% of its final value. 50%, this is called 50%. So the graph is, the response is started from 0, it reached up to 50%. So that particular time is called as the time that is required for the response to reach 50% of its final value is called delay time. And similarly, what is TR? TR is nothing but the rise time. Your TR is called as rise time. It is called rise time. What is rise time? Rise time is nothing but the time that is required for the response to reach 100% of its final value. This is called 100%. This is called 100% of its final value. Therefore, the time required for the response to reach 100% of its final value is called as the rise time. And the third one is the TP, peak time. This is called peak time. What is peak time? Peak time is nothing but here, peak of the response. So this is the peak time basically, where I have, this is what basically, this I have mentioned here, TP. So that is the time required for the response to reach the peak value of that. To reach the peak value is called the TP, peak time. That is the third one. What is the fourth one? That is called TS, settling time. This is called settling time. This is called settling time. What is settling time? Settling time is nothing but the time required for the response to settle within the tolerance band of 2% to the 5% of tolerance band. The time required for the response to settle. That is what the settling time. And there is the fifth parameter that is called peak overshoot. Peak overshoot. MP, that is called percentage of MP, M suffix P, peak overshoot. This is what? That is the difference between the peak value of the response to the this value 1. So that is the difference. That is called difference actually. That is peak overshoot. This difference is called as peak overshoot. The 100% value, the difference of 100% value to the peak value of the response is called as the peak overshoot. This is called your peak overshoot. Okay, peak overshoot. So there are certain mathematical expressions for these time parameters, and in next presentation, and we will see what are the mathematical formulas for this, and definitely 100% you will be asked the questions from these definitions of these times only. What is the rise time? What is the peak time? What is the settling time? What is the peak overshoot for the given second order system? They will give you, they will ask you some question will be given, and for that you need to find out these things. Any of these can be given. So this is the excellent, very important topic in time domain response analysis. All previous what we have seen is that is the introductory part only. Okay, introductory part only. So this is very heart of the time response analysis. This is the major heart. Okay, Yeah, just before this, I have explained you the response. That is the derivation. Don't worry about derivation. Derivation will not be asked in examination. You just remember what is the expression of C of t. That's all. And you, okay. So what is the formula for omega d? What is the formula for what is zeta and what is the definition of zeta? What are the various values of zeta? And then this is very important. This response is very important. And for all these parameters, TD, TR, TP, TS, and MP, there are formulas will be there, and that I will explain you in the subsequent presentation, and we will solve the previous questions also, which are asked in GATE examinations as well as UPSC AES examinations. I am going to solve all the questions of this topic in the next subsequent presentations. So with this, I would like to just close this presentation today. I hope that you have enjoyed this, and request you to give your feedbacks by giving your positive or negative feedbacks, and you can comment on our this thing. And don't forget to subscribe to this channel, that is effective and efficient electronics for excellence. And don't forget to share this thing to your friends. Okay, so we'll close at this point of time today, and we will continue. We'll meet in the subsequent presentation. Okay, thank you, thank one and all. See you.